Investigating acceleration and distance. Physicists define acceleration, A, as any change in the velocity of an object during a time interval. We're going to learn more about this soon, okay, throughout these notes. This little symbol is called delta. This is delta V, which means a change in. Therefore, this is delta T, or a change in the time interval, okay. The change might be an increase in velocity or a decrease in velocity, or the change might be a change in the direction that an object is moving. By analyzing graphs of distance versus time, you can determine whether the velocity is zero, constant, or changing. Okay, this bullet point goes back to our last unit, right? Talking about a distance versus time graph or a velocity graph, right? So we can find out whether something is zero, constant, or changing. You can learn even more from a graph of velocity time. Okay. One thing that just to note is that sometimes position time is used in place of distance time, just so you know. Okay, so first off, we have two graphs here. A position time, so this is our distance time, and this is our velocity time. So how could you describe the slope of the line in graph A? So this is graph A. How would you describe the slope of the line? What does it indicate about it? Okay. Well, you could the distance time graph. So this one here in graph A is a straight sloped line. Okay, which indicates that the velocity is constant. Remember that, right? If we can calculate the slope of a line, a constant velocity, it would look like this. Okay. When you graph the velocity versus time of the same object, the exact same object, you get the graph shown in B. Okay, so this one here, a straight line, a straight flat line, and hopefully this makes a little bit of sense. Okay, this line shows us that the velocity is constant. Okay, so you can see here's our velocity on our y-axis. Okay, and it's constant; it's not changing, right? Same thing here. Our velocity is constant and not changing. But this is when we have a distance or position time, and this is when we have, and right here is when we have a velocity time. Okay, the slope of the line would be zero because the acceleration is zero. There's no acceleration on this graph, right? Hopefully that makes sense. There's a constant velocity here. There is a constant velocity here, and therefore no acceleration. How could you describe the slope of the line in A? Okay, what does it indicate? Okay, what do you think? The distance time graph in A is a curved line which represents a changing velocity. So remember, when we have a curved line, we had a changing velocity in a distance time or position time graph. Okay. Now, when you graph the velocity versus time, okay, or the acceleration graph, it shows that the velocity is increasing at a constant rate, okay, which indicates constant acceleration. Okay, hopefully you're starting, some bells and stuff are starting to go off, some light bulbs, just so you can see the difference, because you will need to know the difference between these two. Okay, and there is differences. Okay, the slope of the line in graph B is rising up to the right, which indicates a positive slope. Okay, if it's rising up, it's positive. Okay, the rise over the run will be a positive number. This means that the object is undergoing a positive acceleration. Okay. Now, how could you describe the slope of the line in graph A? Okay. And what does it indicate about it? Well, this distance time graph in A, the line curves downward. This curve indicates that velocity is changing. In this case, the velocity is decreasing. Okay. If you graph the velocity versus time of the same object, you will get a graph like B. Okay. It's sloping down. Okay. The velocity time graph in B is a straight line. Okay, because we have a constant acceleration. Okay, which again shows the velocity is changing uniformly and acceleration is constant. The difference here is that in this case, the slope of the line is negative. So the rise over the run will be a negative number. Okay, you may have heard the term deceleration referring to slowing down. Okay. Deceleration is not the correct scientific term. We use negative acceleration instead. Okay. Now, calculating acceleration. The definition of acceleration, or A, is the change in velocity, okay, of an object during a time interval. This is a bit of a review from the very beginning, or delta V over delta T. Okay, it's important to use the change in velocity and time for this calculation. Okay, and then here is where I put the delta, or this triangle symbol means delta, and it indicates a change in. Okay, I'm going to provide you with your own formula sheets, so you don't need to take this out for right now. Take out your formula sheet. The formula sheet for acceleration is, however, if you are in one of my classes where I am getting you to write this down, then this is the time to do it. Acceleration is equal to delta V over delta T, or a change in velocity over a change in time. What does that look like? Okay, it's written a couple of different ways you'll find by different teachers, but it's your velocity final minus your velocity initial over your time final minus your time initial. Okay, sometimes this will be written as V2, or the second velocity, minus the V1 over the T2 minus T1. One more thing. With this particular question, you can use the triangle. Remember, if we're trying to find acceleration, we cover up the A, take your thumb and place it over the A, and it's a change in V over a change in T. If you're trying to find the time it took, you'll be given the acceleration and the velocity. It's a change of velocity over the acceleration. If you're trying to find the velocity it took, you'll be given the acceleration and the time, and it'll be acceleration times time. To calculate acceleration, you need three pieces of information, okay, just like before. The beginning velocity, usually called the initial, right, or velocity 1. The end velocity, usually called the final velocity, okay, sometimes called velocity 2, and the time interval during which the change in time happened. A biologist observed a cheetah reach a velocity of 19 meters per second from a standing start in a period of 2 seconds. What was the cheetah's acceleration? Assume the cheetah runs in a positive direction. Okay, so first things first, what do you know? We know the initial velocity is a standing start, so it's going to be 0 meters per second. And the final velocity that was observed was 19 meters per second, and that it took 2 seconds. Okay. This one, I say it's already calculated for you. It's because sometimes you're given a time period, between this time and this time, or this was the end time, this was the time I want you to calculate from, stuff like that. And so we continue on. Substitute what you know in the formula for acceleration. So we have our formula for acceleration, and we need to make sure we grab the correct one. right? We add in our known values, okay, and we should get 9.5 meters per second squared. The cheetah's acceleration is 9.5 meters per second squared in the positive direction. This is because we are dividing velocity in meters per second by time in seconds. So instead of saying meters per second times seconds, we write meters per second squared. So if you've wondered why we use meters per second squared, that's the reason, right? It's right here. We have meters per second times seconds. We're not going to write that. We're going to write meters per second squared.